for coming today. So we have two teams this year for the E420. Team S.A.R.G.E, which is going to present first, and then we will have immediately afterwards Team Sparta. So today is our preliminary design review, so the teams are going to show what they did during the semester. In particular, we focused on identifying all the requirements and specification for our project, and then identify different design alternatives and select the one that better matches all our requirements and specifications. So I will let the Team S.A.R.G.E take over, and thank you for coming.
Thank you, Dr. Gentilini. So as Dr. Gentilini just stated, this is Project Searching West through Ground Explorer, or Project S.A.R.G.E, and this is our preliminary design presentation. So during this presentation, you guys are going to meet the team. We're going to give you some insight into how we made our design decisions for Project S.A.R.G.E. We're going to break down those design decisions into our three subsystems, so mechanical, electrical, and software. And then we're going to talk about our itemized budget and our mass budget. So I'm Jacqueline Worley. I'm the project manager, as well as being a software subsystem team manager. The team is sitting over on the side today, and our mechanical team lead is Grayson Lynch. Our software team lead is Garrison Bybee. And our electrical team lead is Sarah Elabasi. Our mechanical team is also made up of Morgan Baroni and Chad Abramson. And our electrical team is made up of Riley Griffin, and Matthew Todd. So for our overview, we're going to talk about S.A.R.G.E.'s overall goals. We're going to go through our overview chart, and then we're going to talk about the overall system requirements and specifications for S.A.R.G.E. today. So S.A.R.G.E. has two primary goals. The first is to assist in search and rescue. This means that S.A.R.G.E. can be lowered into a mountain search and rescue environment via an aircraft, preferably a helicopter, but if sizes end up changing, it might be something on the size of a C-130 or something like that, but preferably a helicopter. To aid in search and rescue, S.A.R.G.E. will carry 18 kilograms of a payload of survival supplies. This includes food, water, shelter, and medical supplies. S.A.R.G.E. also can lead survivors out to a suitable location. A lot of times in mountain search and rescue, people can get into a place where a person can't necessarily be dropped in to help the survivors. So if the survivors are capable and able of walking, the rescuers can plug in a GPS coordinate location to walk the victims out to a better place for rescue. And we'll talk more about this later during software. Our second goal is that we're competing in the Intelligent Ground Vehicle. No, you're okay. So we're competing in the Intelligent Ground Vehicle Competition, or the IGVC, this upcoming June 1st through the 4th of 2018 at Oakland University, which is in Rochester, Michigan. So this competition is hosted every year. This is the 26th annual competition, and it's broken down into three challenges. What you guys are seeing over here is a description of their auto navigation course. It's about 163 meters long. We have to stay between the lines at all times, or when these lines disappear over here, we have to find our way back to them. All the dots represent obstacles. They range from barrels to ramps with 15-degree slopes. There's some simulated potholes, there's trees, there's lights, there's a variety of things. Hitting an obstacle means we're immediately disqualified. We're also required to stay within a certain range of speeds. We have to stay above 1 mile an hour and below 5 miles an hour. Anything above or below will also disqualify us immediately. We get 2 runs through the course. We first go this way, and then we have to go that way. So that way, if we do try and use our camera to log the course, we have to run it backwards. The second part of our challenge is a design challenge. This involves a paper, a presentation, much like this one, and a poster, and then the judges are actually going to rip apart our vehicle and look into our design process like you guys are today. We're awarded points for every little bit of that, and they stack up the points. We're hoping to get about 85% of those points, which should place us in the top 3, if not winning that part of the competition. Finally, the last challenge is an interoperability profiles challenge. So the judges are going to send a wireless signal to our vehicle. We need to respond within a set amount of time. Every command they send is worth a set of points. Again, we're aiming for about 70% of those points, which should place us in the top 3. If not winning, a lot of teams opt out of that challenge. So our overview chart. As I said before, we have 3 subsystems: mechanical, electrical, and software. Our mechanical is taking care of our locomotion, our structural, our suspension, our steering, and our mechanical e-stop, which is required by the IGVC. Electrical is in charge of our power unit, control unit, voltage regulator, actuators, sensors, and a wireless e-stop, which is also a requirement of the IGVC. And finally, software is making sure we have a navigation algorithm, localization algorithm, a user interface, and a motor control algorithm. So S.A.R.G.E. has several requirements. but there were some that were just too broad to fit into a specific subsection. These are, so we put them in our overall system requirements and specifications. The first is that we need to build the robot entirely by the team. IGVC allows us to start with a pre-made system and build up from it. Because this is capstone, we wanted to start from scratch, build from the ground up, so we get to learn every aspect of it. The second is to stay within budget. We have a total budget of about $6,000 for our robot. That includes money from URI, thank you very much, the College of Engineering, and a private donor. Our third is to complete an IGVC course run. A lot of teams go to the IGVC and they don't even make it through the course. Last year, the third place winner made it 44 feet into the course. So our goal is to at least make it around once. And hopefully after that, beat the time from last year, from the team who didn't make it around. Our fourth, as I already talked about, is our search and rescue purposes. We really want this to be something that will work after capstone, not just a competition oriented. And as I already stated, that includes having the payload of survival supplies, having the ability to walk survivors out within a 1.5 kilometer range, and then being able to create communication between survivors and rescuers in a 50 kilometer range, probably through a walkie-talkie or something like that. And then finally, our last requirement is to win the competition, which is a very vague statement. But that means completing the course in under 4.01 minutes, because that was the winning time last year for IIT Bombay. We want to get 85% of our design competition points and 70% of our interoperability profiles challenge, which hopefully again should place us at the top. And now I'll pass it on to Sarah to talk to you guys about our design decisions.
Thank you, Jackie. So now I'm going to talk about the process we use to choose our final design. So first we ranked our subsystem requirements. Then we used the morphological chart to identify our different alternatives. Then we use a decision matrix to rank those alternatives. And finally, we will talk about our final design. So here's a table we use to rank our subsystem requirements. So we have probably around 30 requirements, and we only decided to choose these 12, which are suspension, steering, structure, power, drivetrain, maximum current draw, battery capacity, safety, autonomy, control unit, and user interface. So we thought these 12 requirements are the most important to pick our final design. So to explain this table a little bit more, we're going to pick an example, which is the control unit. So here you can see that in the first cell, we evaluated the control unit with the drivetrain, and we gave it a 1. We did the same thing for the suspension and structure. And then for number 4, we evaluated the control unit with the drivetrain, and we thought the control unit was less important than the drivetrain. Therefore, we gave it a 0. So after that, we just sum up the row, and then we end up with the total score. The maximum total score we could get is 11. So for the control unit, we got a score of 7. So in this table, you can see that the budget has the highest score with an 11, and safety has the second highest score with a 10. So these total scores will help us rank the requirements. So here we can see that budget and safety have a percentage of 20%, the drivetrain 15%, 7% for control unit, autonomy, and maximum current draw. We give 6% for structure and power, 6% for battery capacity and steering, 3% for suspension, and 1% for user interface. And you can see that the total comes out to be 100%. And now I'll pass it on to Matthew.
Thank you, Sarah. So once we assigned an importance to each of our requirements, we came up with a morphological chart, which is just a visual way of displaying all the different options for our 3 design paths. We have our first design path is shown in green, our second design path is shown in blue, and our third design path is shown in red. And this can be found in page 5 of your handout. So for example, our first design path is using a red button for a mechanical e-stop, Raspberry Pi for a wireless e-stop, the TI C3200, also known as a launch pad for our Wi-Fi communications, brushless motors to operate wheels, pulling 400 amps, using optical cameras for stereoscopic algorithms and a LiDAR for optical flow algorithms. Infrared cameras for detecting heat sources. 5 milliseconds timing on processing the images. A Raspberry Pi to process those. An inwards layout for the chassis. Metal for the chassis. And plastic. 18 kilograms supported. 2,000 watts power drawn, lasting 2 hours. Linear actuated steering. 4-link suspension. And a computer for the user interface. And then to reiterate, design path 1, which is shown here, would be using the Raspberry Pi and TIC3200 for Wi-Fi communications, brushless motors to operate the wheels, pulling 400 amps from the battery, LiDAR optical cameras for stereoscopic and optical flow algorithms, a metal and plastic build and supporting 18 kilograms of payload. The second design path that we considered, shown here, is using an Arduino Mega and PIC microcontrollers, DC motors to operate the tracks, 300 amps being pulled from the battery, LiDAR to incorporate optical flow algorithms, and then infrared sensors, and then using a composite and plastic build supporting 9 kilograms of payload. And then our third design path that we considered, which is shown here, is using the Raspberry Pi and BeagleBone, using AC motors to operate the wheels, pulling 200 amps from the batteries, using optical cameras for the stereoscopic algorithms, and then infrared sensors, using a metal and composite build, and then 18 kilograms payload support. And then I'm going to pass it back off to Morgan, who's going to summarize our design paths.
Thank you, Matt. Once we had our morphological chart and our 3 design paths, we had to determine which design path to implement. To do this, we first assign each component or criteria a score. So we will continue to look at the control unit example, which you will see the Raspberry Pi was used for path 1 and 3, the BeagleBone was used for path 2, and the Arduino Mega was not used. For the Raspberry Pi, we gave it a score of 9, which according to our rubric on the right means that is an excellent solution. This is because the Raspberry Pi operates at a frequency of 1.26 gigahertz, which is approximately 2 times our minimum specification of 700 megahertz. Meanwhile, for the BeagleBone, we gave it a score of an 8, which once again, according to our scale on the right, means that it is a very good solution. The BeagleBone operates at 700 megahertz, which means that it meets our minimum specification. However, because it operates at less frequency than the Raspberry Pi, it was given a lower score. Once we gave all the components and criteria a score, we assembled a decision matrix, which you will see in page 6 on your handout. We then had to determine which path to use. To do this, we multiplied each score for the component or criteria by their associated weight, and to give us a utility score. Continuing with the control unit example, you will see that for design path 1 and 3, we gave it a score of 9, multiplied by a weight of 7% to give us a utility score of 0.63. For design path 2, we give it a score of an 8, once again multiplied by 7% to give us a utility score of 0.56. We did this for each of the components and criteria respective to their design paths, and then summed up the each design path's utility score to give a total utility score. We then determined which design path had the highest total utility score, which, as you can see, is design path 1, which has a total utility score of 8.80. Therefore, we chose this design path to implement, which you can see is stated here and was stated previously. Additionally, it will have a 4-link suspension and a linearly actuated steering system. And I will now pass it off to Grayson for the mechanical subsystem.
Thank you. So as stated, this is the mechanical subsystem overview. In this overview, we'll be speaking about the mechanical subsystem components, as well as the mechanical subsystem design. In the design, we'll talk about the computer-aided design, or CAD models, the finite element analyses, or the FEA, the kinematic simulations, the motors, as well as the steering system. After that, we'll speak about the requirements and specifications that have been met by the mechanical team. For our components, we took into account mainly safety when we were developing this vehicle. Since we are developing it in order to help people, we would like to limit the amount of harm we could possibly do to someone. After that, we took into account locomotion and the structure system. Here's a current CAD model developed inside CATIA for our prototype. As you can see, well, I'll explain. The dimensions of this vehicle are 1.34 meters long by 1.04 meters wide and 0.66 meters tall. In this model, we have a cargo area shown here in this blown out view that has an area of 0.127 meters squared and a total interior volume of 0.06 meters cubed. The unladen mass is 48.6 kilograms for this vehicle. For the finite element analysis, we looked at 4 main components that we'll show in this presentation today. We took into account welds for this to get a more accurate simulation. So we implemented fillets into the model, and then we also assigned the correct materials to each of them. For this first one, we used an aluminum T66061 and also implemented this cross section here throughout. We found, we were analyzing to see if we were within our requirement 2.10.2, that we would be able to support a maximum payload of 18 kilograms. So that's what we implemented as a 222 Newton force, shown here. We found in this analysis that the maximum von Mises stress was 26.2 megapascals. The aluminum that we have chosen yields at 240 megapascals, so that gives us a factor of safety of 9.16. For our second finite element analysis, we looked at the roll cage. Specifically, we wanted to make sure that our roll cage would match our requirement 2.12.1, that our vehicle would be compliant with the military standard 810C. This requirement specifies that a vehicle of our size must be dropped from a height of 0.6 meters or lower and still be fully functional after the drop. So in order to account for this, we dropped it from the back on top of the roll cage at the weakest point shown here. And this is the entire mass of the vehicle on this thing, so that comes to about 1,040 newtons of impact. We dropped it from a height of 0.915 meters to take into account any extra, and to make sure that we will fulfill our requirement of 0.6 meters. The maximum von Mises stress found in this analysis was 165 megapascals, and this roll cage is made from a steel that has a yield stress of 250 megapascals. This gives us a factor of safety of 1.51 for our design. For the third finite element analysis, we looked at the axle. We wanted to make sure that the axle will be able to support our robot at full load statically, and we found it was able to. We found that, we calculated that the axle would have 400 newtons of force on each tire when at full load of the robot. So the maximum von Mises stress was only found to be around 6 megapascals. The aluminum is the same aluminum we used in the chassis with the same cross section shown here. And it had a yield stress of 240 megapascals, so that gives us a factor of safety of 40 for this part. Should be plenty enough. For the suspension, for the final finite element analysis, we looked at the total suspension system inside of ANSYS. We wanted to make sure that the linkage arms shown here would be able to withstand the inertial forces of the robot at full speed and at maximum turn. So that's 2.2 meters per second at 50 degrees turn on the wheels. And we calculated that the inertial forces in the body would be 138.2 newtons, which we distributed along the force here. In this calculation, we found the maximum on MESA stress to be around 55 megapascals. And again, these links are made from the same steel as the roll cage, which has 250 megapascals of yield stress. So this gives us a factor of safety of 4.5. I'll now pass it on to Chad to speak about the kinematic simulations.
Thank you, Grayson. So we ran some kinematic simulations of our robot on MATLAB, and the kinematics code shows the wheel speeds on a full turn going to a straight turn. Being that each wheel is independently driven by its own motor, we are implementing a software-based differential instead of a hardware or mechanical differential typically seen in automobiles. We are also putting the steering system on the rear axle. So this robot is undergoing a left turn in the simulation, even though it shows that the wheels are turning right. So in this simulation, the right side tires are shown in red, the left is shown in blue, and throughout this left turn, the right tires are moving faster than the left, which is as expected. So we know that our simulation is correct. These two graphs right here show the linear velocity in meters per second, and these two show the angular velocity in radians per second. So the turning radius was determined to be a maximum of 50, it was calculated off of a maximum steering angle of 50 degrees. We determined this by cranking the wheels over as far as they would go in the CATIA model and just checking for interferences. With this 50-degree steering angle, we have a resulting turning radius of 1.23 meters, which satisfies our specification 2.3.1, where we say the maximum turning radius will be 1.3 meters. So here is an animation of the kinematic simulation. The animation source code came from Dr. Mark Compare, a professor at Embry-Riddle-Daytona. The parameters we changed on this code are the critical dimensions of the robot: length, width, height, and tire size, and changed the steering axle to the rear, which was accomplished by modifying the translation matrix. So the purple dotted line shows the center line of the front axle, and the light blue line, a little hard to see, but that shows the center line of the robot itself. And you can see that they are offset, so our simulations are moving as we expect. So for our motors, we are going with RacerStar 6368 brushless DC motors. We will be attaching their output shafts to a planetary gearbox with a gear ratio of 100:1. The resulting peak torque per motor is then 169.5 Newton meters, and the nominal or just standard operational torque of these motors is then 59.3 Newton meters. The total nominal torque of the robot multiplied by the 4 motors we will be using on each wheel comes out to 237.2 Newton meters, which satisfies our specification 2.2.2, where we say the actuators shall move the robot with a total minimum torque of 160 Newton meters. For the steering system, we're using an electronic linear actuator from Fergelli Automation Incorporated. This linear actuator has a maximum pushing force of 750 newtons, and it moves at a speed of 7 millimeters per second. This linear actuator satisfies our specification 2.3.2, where we say the steering system shall have a minimum force of 200 newtons. Now I'll pass it off to Grayson to wrap up the mechanical subsystem.
Thanks, Chad. So this can be found or read out on pages 2 through 4 as the requirements specifications. We'll be looking here at the mechanical column. So for the first, we were under budget, so that satisfied that requirement. We have a practical locomotion system. Our steering mechanism is on the rear axle. We have satisfied our structural component. The suspension is being designed in order to accommodate the requirements. The mechanical e-stop is located on the rear of the vehicle as a large red button. We are within IGVC dimension requirements and will be able to traverse uneven terrain. We have followed along with IGVC speed requirements and any other requirements throughout the development of this vehicle, so we satisfied that. And we will be able to carry a payload from 9 to 18 kilograms. And also we'll be able to go up the gradient of 44% with our chosen motors and gearbox ratio. We'll also be IP56W compliant with the body materials we're using for this vehicle. And we'll be drop resistant to the military standard 810C. I'll now pass it to Sarah to talk about the electrical subsystem.
Thank you, Grace. So now we're going to talk about the electrical subsystem with its components, and then we're going to talk about the design, including the motor driver system, the motors, the battery, the cameras, and the sensors. And then we're going to see if we have met our requirements and specifications. So our four main components are safety, power unit, control unit, and sensors. So here's a general schematic of our design. So we have the battery right here, and it will go through a power distribution unit, and it will distribute power to all of our components. Then we got the control unit over here. It will get data from the sensory unit. After processing that data, it will pass it on to the steering system, and then to the motor driver system. The motor driver system has 4 actuators. And for safety, we have an e-stop, mechanical and wireless. And that's for any kind of safety. If we want the robot to stop moving for any reasons, it will cut off any communication between the power and the motors. And now, Randy Griffin will talk more about the motor driver system.
Thank you, Sarah. So for the motor driver system, first we have the battery. And on here, we are using 24 volts. And that 24 volts is going to be sent through a low dropout regulator, or an LDO. The reason for using an LDO is because they're typically pretty good at mitigating a lot of noise. And with all the motors and electrical sensors that we have on there, we anticipate that we're going to have a lot of noise. So we're using an LDO to compensate. From there, that's going to be used to power the TIC3200 as well as the Raspberry Pi. On top of the Raspberry Pi, we're going to have a pulse width modulation generator, or a PWM module. And from there, that will pass a PWM to each of the electronic speed controllers, or ESCs, which in turn will power each of their individual motors. Again, for the motors, we are using the Rochester 6368s. They're rated for a KV of 280. KV stands for revolutions per minute per volt, and this results in 8,400 RPM at 30 volts, which is the highest voltage that we are going to be running. The motors are rated for 18 volts to 50 volts, which falls above and below the range of the battery. They are rated for 480 watts nominally at 20 amps, and they will peak 1,440 watts at 60 amps. For the speed controllers, we are using the VESC FOC ESC, which stands for Field Orientation Control Box. Those are also rated for 12 volts to 50 volts, which falls within the range of our battery. They're able to supply 60 amps continuous, as well as a 120 amp peak for 10 seconds. This satisfies our requirement of 3.4.1, where a minimum of 1,600 watts shall be supplied to the actuators. This is a sample motor test that we ran. So the blue line is the current into the ESC, and the red is the corresponding current that is supplied to the motors, and the green line is the duty cycle that's being sent as a PWM into the speed controller. Right here, we attempted to do a stall on the motor, and that's why there's a large current spike, and it spiked up to roughly 10 amps. And as a result of that, this was the RPM of the motor. And you can see that right here at this spike, there's almost no change in the RPM. So that shows us that the motors are very capable of handling a high stall torque. So here are the two charts side by side as a little bit of a comparison. So we started at 1,000 RPM and jumped up by 1,000 every time until we went up to 6,000. And then that's when we attempted to do a stall as far as the power supply would let us. And then Again, here's the current spike, and here's the output of what is happening to the actual motor. So as you can see, even though there was we attempted to stall it, it did an outstanding job of maintaining a stable RPM. Now I'll pass it off to Matt to describe more about the battery.
So how we plan on implementing our battery design is with small cells that are approximately the size of a AA battery. Each of these cells, depending on how charged it is, will range anywhere from 1 to 1.5 volts. There will be 20 of these cells per pack and then 6 packs in parallel, which should give us our required wattage of 680 for this specification. And then a voltage swing, depending on how charged it is, anywhere between 20 to 30 volts, which will satisfy our 22 volt specification. And then having an amperage of 414 amps, 414 kilojoules, which will satisfy our specification here of 250 amps. Here's a brief description of the sensor functions that we're going to plan on implementing on our robot. We have optical cameras are going to be used to detect the path and color. Infrared cameras for heat signatures on detecting victims. Short-range infrared sensors to detect cliffs and on the underside of the carriage for cliff sensing. And then long-range infrared sensors just as a last resort before we bump into anything, because that will automatically disqualify us in competition. And then a LiDAR is going to be used as our primary means of detecting the obstacles in the course. And then more information on the cameras. We have 2 optical cameras. We're going to be using the Raspberry Pi cameras. And they'll be giving us 62.2 degrees of a horizontal view, which satisfies our subsystem requirement needing 50 degrees. We'll also be using 1 infrared camera, which is 51 degrees, satisfying our requirement, our specification needing 45 degrees. And then we'll be, this is more information on the infrared sensors we'll be using. Again, the short range sensors will be on the undercarriage for cliff detection and are from 10 centimeters to 80 centimeters, satisfying our specification of 10 centimeters to 80 centimeters. And then 12 long-range infrared sensors will be 1 to 5 meters, satisfying our specification of needing at least 1 meter to 5 feet. Lastly, our LiDAR is going to have a horizontal view of 100 degrees, satisfying our specification of 70 degrees. It will operate at a range of 6 to 9 meters, which satisfies our specification of 6 meters. And I'm going to pass it back off to Sarah to summarize our specifications.
So as you can see here, and you can also find this table on page 2 of the handout, we have met all of our specifications. So our vehicle, the electrical subsystem will be under $3,000. And we have met the specifications that are in relation with the IGVC. So the power, the actuators, and the voltage regulators. And also for all the sensors, we have met all the specifications. And also for the control unit and safety. And for the search and rescue purpose, we also have met the specifications regarding the power and sensors. And of course, safety and having a design that is weather resistant and drop resistant. And now I'll pass it on to Garrison for the software subsystem.
Thank you, Sarah. So I'm going to be talking about the software subsystem components, design, and then we'll be going over if we've met the software subsystem requirements and specifications. So the design consists of the navigation and localization algorithm, the motor control algorithm, a graphical user interface flowchart, and then a demo for the graphical user interface prototype that we have, and a demo of the LiDAR prototype. So again, the software subsystem components consist of the navigation and localization algorithm, the motor control algorithm, and the graphical user interface. And then, as you can see here, this is a prototype of our graphical user interface that's been made in Python. As of right now, it's very simple, but you'll see that later in our demo. So to go over the navigation and localization flowchart. So when the system first boots up, it'll start receiving data from the LiDAR, the GPS, and the IR, and the cameras. It'll then take that data and convert it into a point cloud map. It will then check to see if the GPS position as designated by the user has been met. If it has, it will then alert the user, and it'll enter low power mode and shut down. If it has not been met, it'll start to detect and see if there are objects within 3 meters. If there are no objects within 3 meters, it'll send a command to the motor control algorithm, which you'll see in a second, for forward, and it'll then continue to loop through until it does detect an object within 3 meters. If there is an object within 3 meters, it will then determine the direction in which it needs to go by determining where the object is, and then either needing to go right or left. It will then send that command to the motor control algorithm once again, either right or left. It will then check again to see if the object is 0.5 meters away, because we don't want to hit anything. And if the object is 0.5 meters away, we will send a command to the motor control and go in reverse. If the object is not 0.5 meters away, we will continue to move forward as specified and then continue through the loop. If after the motor has gone into reverse, it will then check to see if the position has moved. And if the position has not moved, we're assuming that the robot is stuck. We will then alert the user and enter low power mode. If the position has moved, we will then send another command to the motor control, and we will continue to move forward. And now the motor control algorithm. So as I stated before, it'll come in from the navigation and localization algorithm. It'll either have forward, reverse, left, or right. So if it goes forward, you can see here all the motors will stay constant. All the speed on the motors will stay constant. It'll continue to move forward, and then it'll pass control back to the navigation and localization. If reverse comes in, it'll just then shift all the motors into reverse, and then again send back command to the other algorithm. And then left or right, so if right comes in, it will decrease speed on the right side. It will then activate the linear actuator, and it will then go back and pass control back over. If it's on the left, it will decrease speed on the left side, and then it'll activate the linear actuator once again, and then go back to the user. So I will now pass it on to Jackie to talk about the graphical user interface.
Thank you, Garrison. So as previously stated by myself and by Garrison, we do have a graphical user interface. It is going to take the form of a very simple program on a laptop. The way this works in our algorithm is that the GPS position, the battery level, and the speed are all read into it. It will then display this out to the user. The program then checks to see if the GUI has been closed at any point. If it is, it'll stop bringing in data. If not, it'll constantly keep bringing in that information. And then it will also check to see if the e-stop has been activated at some point, so that way if we lose contact with the vehicle for some reason, we know the GPS location at last was. And it will keep continuously storing all this information, because as again, we are putting this into a search and rescue environment. We need to know where it is if we lose contact. This is a very short demo of our graphical user interface. Right now, the refresh just resets the GPS coordinate, the battery level, and the speed. When this is actually hooked up to our vehicle, those will be continuously updating as long as this program is open. The new GPS target is, as I mentioned before, S.A.R.G.E can lead victims out to a safer location. This is what the search and rescue would plug in. And it was about the new destination telling our vehicle to go to that position. Open is what pulls up a list of all the past GPS locations, so we can always find it. This is a demo of our LiDAR. We fortunately did receive this recently and have been doing some preliminary investigation into it. It's a little hard to see, but these white lines that are moving are us moving in front of the LiDAR. It's a little easier to see on our graph. All these dots are ourselves or computers or various objects in front of the LiDAR. It is spitting out the information we would expect, which is a distance to each point and an angle to it. So we can navigate around the obstacles that we are going to approach in both the competition and in the search and rescue environment. I'll now pass back to Garrison to talk about our requirements and specifications.
Thank you, Jackie. And you can see these requirements and specifications on page 2 and 3 of your handouts. And so We came in at budget because we didn't have a budget, so it was $0. And then the autonomous system, as we've designed it right now, will meet all of the requirements that we have specified. The IGVC, for the IGVC, we have the wireless communications. The launch pad that was chosen by the electrical team meets the software requirements for this. And then, so same as the sensors that have been chosen, they will meet our, they have so far have met our requirements that we have chosen. And now I'll pass it off to Chad to talk about the itemized budget.
Thank you, Peterson. So this table can be seen on page 8 of your handout. This is an itemized budget of everything that we will be purchasing and putting on our robot. The most expensive items in this list are the wheels and tires that come up to $400, the infrared camera comes up to $500, and our LiDAR comes out to $600. So overall, we will be spending $4,884.47, which is well under our allotted budget of $6,000 for constructing the robot. Here's a breakdown of our overall funding. So in total, we have $10,300 to use. $8,000 of that was awarded from URI, $1,300 from the College of Engineering, and $1,000 from a private donor, Michael Brennan. So the funding is divided into the $4,884.47 to actually build the vehicle, and $1,115.53 for just additional extra charges that we might come across when prototyping the robot. And the remaining $4,300 will be used for travel expenses for the IGVC competition. Here's a table of our mass budget. It can be seen in page 9 of your handout. The heaviest items on this list are the wheels and tires, which come out to a whopping 25.4 kilograms, and our battery, which comes out to 6 kilograms. So in total, our robot will be weighing 48.6 kilograms. Now I will give it to Jackie to wrap it all up.
Thank you, Jack. So to summarize what we just went over, we talked about S.A.R.G.E's overview and its goals, the IGVC, and our search and rescue purposes. We discussed how we made the decision process, how we decided our design going through that entire process. We talked about our preliminary design broken down into our 3 subsystems, mechanical, electrical, and software. And finally, we discussed that we did in fact meet all of our requirements and specifications as set forth at the moment. We'd like to give a really big thank you to URI and the College of Engineering, and to our private donor, Michael Brannon. Without you guys, we definitely could not pull off this project. It's expensive. And we'd also like to thank numerous amounts of our faculty and staff who have supported us, given us advice, and just overall been there for us as we've been figuring all this out. And that's it. Thank you very much for attending and listening. And if you have any questions, let us know.
Morning, everyone. I don't think I need the microphone. Pass with it. Can you hear me at the back?
Yeah.
They have the opposite problem. So congratulations, by the way, in being one of the first groups that I've seen do what I would consider as on the path of system engineering analysis. That's not a very common thing that I've seen. It's a fairly new discipline. I think you guys did a reasonable job there breaking it down from a system engineering perspective to try and weigh the paths that you were following.
Thank you.
Thank you.
So a couple of questions as I went through. One of the first things that popped out to me was the power budget. I saw that we did somewhat of an analysis on the power requirements per motor based on the payload and so on. Let me take that a little higher, if you will, and ask, how long could your robot go with a full payload in a moderate worst case scenario given the batteries that you're choosing?
That's a great question. Thank you. I'm going to pass you to our electrical team to answer that.
Okay, so how we did that calculation is we basically The robot, we did a requirement that, one of our specifications was that the robot needed to go up a minimum of a 40-degree incline. So off of that incline, we did a force calculation to say if it's going to be going up a 40-degree incline, how much power is it going to take to basically move it up at 5 miles an hour at the max speed. So we picked a worst case scenario and did our calculation based off of that. So with all of the power coming from the motors through the gearbox through an 18-inch wheel, we did the calculations for that and figured out that we needed at least 1,600 watts to move the vehicle at 5 miles an hour up a 40-degree slope. So your question is how long will the robot run?
Let's use that worst case scenario.
Yeah.
In that worst case scenario,
Yep.
how long can I keep going? Can I actually go the 180 some meters at that speed?
Absolutely. So with the longest the vehicle can run at worst case scenario, it consumes roughly 300 kilojoules per hour of operation, and we have 414 kilojoules available just because of the power requirement of the amp draw from the battery. We had a capacity higher than what we actually needed, so we can run for roughly an hour and a half at worst case scenario, going uphill at 40 degrees with a full payload.
Considering losses, et cetera, and efficiency
Yes.
and so on.
Yep.
So you have about 2-3x margin.
Yeah.
Okay, good. That's all.
A small edit to your answer, it's a 40%, right? Not a
Sorry, that one. Yes.
14.
Yes.
Okay, yeah, 40 sounded a wee bit aggressive, but. Neat. Quick comment on that too, having built one or two of these in the past. You might want to consider a secondary battery system for the electronics.
Mhm.
Because the high power stuff is horrific in the noise that it passes through
Yep.
to the low power electronics, and you will run into problems.
Yep.
So, from the onset. So think about that and things like opto isolation.
That's what we were thinking about. Yep.
On the flip side, the navigation stuff, it sounds like for determining where you are and being able to react to questions like where am I pointing, my heading, so on, am I moving? It sounds like you're wholly dependent on a single point of failure, being the GPS. Is that a correct assessment?
You're asking if we're depending on our GPS completely?
To determine where you are, it sounds like your only navigation sensor that can provide you with that information is the GPS, correct?
I believe so at this point. Garrison?
That's correct.
So that's your single point of failure.
Yes.
I guarantee you'll have to come and address that problem.
Yeah.
But the single point localization, navigation sensor, pardon me, doesn't seem like it's going to be able to provide you with your position at a level of fidelity that you need to be able to answer some of the questions that you've asked. Because they're typically only going to give you 2-3 meters, 1 signal. And that doesn't sound like it's good enough. The reactive path planning stuff that you're doing, I think you're okay with the LiDAR. The infrared sensors, anybody test those things outside?
Not yet.
There's this really bright infrared source up in the sky that doesn't like plain, it may flood those sharp sensors. The last time I took them outside, it didn't work so well. There's one other modality that's very common outside because it doesn't care about light. Anybody know what that is?
Sonar.
Yes, ultrasound is very reliable outside, phones doesn't bounce into. So you must take a look at the navigation sensor. You're going to be in trouble with just the one GPS alone.
All right. Thank you for your perspective.
Thank you guys.
Yeah, thank you.
Nice job this morning. Pass it on.
I just got 2 quick questions.
There we go. I have 2 quick questions. One's on the budget. You've got $4,300 left for travel. Is that going to be enough for all of you to travel, or have you looked at that budget at all for travel expenses?
That budget is planning for only having 2 students go. It is during the summer, so most of us have internships, golf commitments, or other various objects. So it's just planning on having Dr. Gentilini going with us and 1 to 2 members of the team.
Okay, sounds a little more reasonable than sending all of the second. And then the second one, I'd like to look at the motor that Riley was showing the stats on when they tried to stall it. So if you got the curves, I don't know what slide it is. But anyway, you have nominal at 20 amps. I think.
Yes.
So is that the,
Oh, really?
there we go. Is that, so 20 amps, is that about where you're trying to run it?
Yes. Okay. So the reason why this is not at 20 amps is because this was using one of the lab bench power supplies. So did not like supplying the amount of current that we were trying to push into it. It would click and get angry, and it just did not like it.
Okay.
So I did test it separately with a 6S LiPo, and it did feed back roughly 20 amps no matter where the RPM was.
Okay, so I guess what I'm looking at here is you did the bench supply, you maxed out the bench supply.
Yes.
But that may not be realistic as far as what you're going to see in the real world, because you were only getting 10 amps and you're expecting to be pulling 20 to 60 if I was looking at
Yes.
data, right?
So
Okay.
this was a very early preliminary test just to see that the ESC and the motor were responding how we would expect them to.
Okay, so just make sure you get that testing done out in the real world
Yeah.
with the amount of amps you're
Yeah,
expecting.
this was also no load and just the motor sitting there on its own. So there was no gearbox, there was no tires, there was absolutely no load.
Okay, thank you.
Thank you.
So on the charts regarding the selection of the design path that you chose, there were 3 design paths and roughly 10 or so subsystems being evaluated on each of those. The choice on many of those subsystems I would expect to be independent of each other. So the number of permutations of design paths are much larger than 3.
Yes.
How did you get down to 3?
Dr. Gentilini told us honestly to pick 3. So we tried to pick the ones we thought would be most logical. And we sat there and debated back and forth between each other what we wanted to use, why we wanted to use it, and spent about 2 weeks going back and forth, coming up with a whole list and narrowing it down to what we thought would be the most useful and the most likely to work.
So was there any
We can hear you anyway, sir.
Was there any consideration given to evaluating which subsystems were independent of each other, which decisions were independent, and then doing a subsystem level optimization across the many selections?
I think maybe a little bit subconsciously, yes. I think mostly it was just, we know these things should work, let's try them, let's test them out, and using our knowledge from past classes, let's go forward with these.
Thank you. And one other question, there were, in each of the subsystem presentations, you alluded to the design specification, but it wasn't clear to me where those requirements came from.
So if you look in your handout, actually, we have an entire document, our specifications and recommendation, our sheet that will break down where all of those came from. That's the very first step of the planning process as set up by Dr. Gentilini. He had us go through and decide what all of our requirements were for the entire vehicle, for this entire process, and then coming up with the specifications off of that, and then building from that our design process.
Thank you. I would suggest that for these presentations, that the reviewers are looking to see, okay, did you meet the requirements? I would suggest for each subsystem, start by listing, these are the key requirements and some hint as to where they came from, and then introduce how you met those. So, obviously, there's going to be a lot more requirements than you can address, so by showing where they came from and indicating that this was identified as the critical one, and then address how you met that requirement.
Okay, thank you, sir. We'll definitely incorporate that.
I have a couple questions. So you indicated mill standard 810C for Rochester. Why?
It's a good standard to work off of. It's one that the military uses, and we knew because we're hoping that the search and rescue would be picked up by someone like the Coast Guard or a military organization. It's a good one to base our knowledge off of. Grayson can definitely talk a little more about it.
Yeah, it's a very common standard used in like phone cases and stuff today for consumer things. So that's what we decided to choose for a robot. Hopefully the standard goes up to something of our size, not just a phone case. And stated that we should drop it from 0.6 meters, and then if it works after that, then it meets the requirements, and it'll we can say it's military standard ruggedized.
Okay. You also talked about IP56W. What's that?
So that is our weather resistant, which Grayson can talk more about as well, or I can discuss
I
it.
believe actually Morgan.
Oh, Morgan, my apologies, Morgan.
So each number means a certain condition that the vehicle must withstand. So for example, basically it needs to be dust, all the electronic protected. And then we need to be able to basically hit it with a hose at high pressure for 3 minutes. And it needs to be able to protect all of the electronics and still be able to function, and then meet a certain temperature range, which is about negative 23 degrees Celsius to 38 degrees Celsius.
How do you plan on testing for the dust requirement?
Fortunately, we live in the desert, so we can take it outside of Prescott Valley, out by the Mavericks, where the dust storms kick up, and see what happens.
Last question. So many of the cameras require 5 volts. So how do you get the 5 volts out of your 12 volts battery source?
Great question. I'll pass it on to our electrical team, primarily Riley.
We're going to have several LDOs, each one for each voltage, because the LiDAR, the battery is 30 to 20 volts. The LiDAR is 12 volts. And then a lot of this isn't the only sensor. All of the IR sensors are also 5 volts. We will have an LDO for basically every voltage. And then because now that we've finally finalized the number of sensors, and if we do have to go back and switch to ultrasonic if they don't work, we will pick an LDO based off of the power needed to run everything.
Thank you.
Thank you.
I have a few questions. First of all, on slide 31, do you know the constraints, and do you have the kinematic model for your, maybe it's not there, maybe it's 32, the kinematic model for your robot? Or are you just using the simulation that you've got from Daytona?
That is a great question. Let me pass that on to Chad and Grayson to talk about that.
So I developed the code for the kinematic model. The simulation only did a simulation just so we can show it off in this presentation from Dr. Mark Comper in Daytona. But those graphs are from my own code in MATLAB, and we will be using these in real time with our robot to use as the software differential. Does that answer your question?
I think so. Slide 37. I have it in my slide. Yeah, that's right. All right. Is that a schematic or a block diagram or a hybrid? Both?
I will pass that question along to Matt. He is the creator of that.
It's more of a block diagram. It's using a schematic software, but given the limitations of the schematic software, we tried to create this most accurate of a block diagram as we could, giving it as much detail as the schematic would give.
Okay, I think the information's there. You might want to consider presenting it differently.
Okay.
Thank you, sir. We will definitely work with that.
Let's see, 39, this maybe I should be giving you more benefit. Is the block box, is that reversible?
Yes.
Okay, good. Just wondering, because a lot of those are made for.
Yes, single direction.
Single direction, okay. On 42, how will stall apply to?
Basically, we had it hooked up to a plate that was mounted to a bench vise, and then we basically, we couldn't fully stall it, otherwise the power supply would turn off or get mad, but basically we pressed on the housing and just created some friction on the housing just to spike the current so we could see what was going to happen on the output.
Slide 45, and this is probably my ignorance. Can the Raspberry Pi handle 2 iCams?
Yes.
They can? Okay, do you have the processing capability to do that?
So the standard Raspberry Pi technically only has one breakout on it, so like a Raspberry Pi board. There is a secondary, you can support a second Raspberry Pi camera, but it's not natively on board on the normal Raspberry Pi board, but you can break it out from the GPIO.
And this next one goes back to what Dr. Ruder was saying. If you use IR sensors using sonar, you may want to consider rotating through rather than having them all peeking at constant speed on all motors actually equal forward motion? And is there another way you could, if the answer is no, fix that?
Well, so I don't have a lot of experience in robotics, but as understood by talking with the mechanical team, yes. So I might want to pass it on to Grayson. I don't know if you have any input into that.
Well, I'm assuming your constant speed on all motors means that they'll stay at a constant speed and not just be spiking all over.
Yeah,
the
they'll
place.
stay at the speed that they're
So
at.
the right one, if we're making a left turn, the right one will have to spin faster than the left. So it'll be constantly faster than the left one.
I don't know if that is.
I think we mean consistent.
Yeah.
So is there another sensor you could use to actually determine whether you're going forward or turning?
Well, the object, yeah, I mean, if we've detected an object, then potentially it'll be getting closer if we're going forward. Or if there's something off to the side, we can use that as a point of reference.
You could also consider radars, which just give you some information on even velocity on the vertical axis. That would be probably better feedback.
Okay, thank you.
Just this command system motors. But other than that, good job.
Thank you.
Like the
Dr.
presentation.
Davis, do you have anything? I saw you raise your hand a couple times since we have a minute or so.
I wasn't sure when you were calling time. Really quick question, Kevin. First off, as other people said, very nice job. To reiterate, but in a little bit different way than Professor Gruder did, you could do better tracing your requirements from arbitrary magnitudes back to the fundamental requirements. So specifically, could we look at requirement 3.7.1, which is your 700 megahertz CPU requirement? Can you tell me how you derived that?
I don't know, we'll pass it off to my electrical team.
I'll pass it off to Matt.
That question's been asked before, and that's a very nice question, a very tough question to answer too. It's mainly comparing different results that we've seen from other users out in the field and what kind of image processing they can achieve with it. And it was more or less, since we don't have a cycles per instruction count or anything like that to base software timing results with, we're looking at the actual image processing, just a generalization of what we're seeing as feedback from other people that we're seeing just out in the engineering community. So.
Okay, I'm confident you're aware of that, and you answered the question very well, putting it back to the image processing, but the part that was most bothersome about the presentation is you seem to make an apples-to-apples comparison between a Raspberry Pi at 700 and a BeagleBone at 700. If the Raspberry Pi is running at 700, the BeagleBone is going to have to run at 3.5 gig to be equivalent.
Correct.
Okay, so you can't make apples-to-apples comparisons.
Correct. Our BeagleBone design path is actually not using optical cameras as its mean for image processing. It's mainly using points that it's collecting as a vector from the LiDAR to do some more mathematical operations rather than doing the heavy CPU load of image processing that the Raspberry Pi was expecting to accomplish. So.
Overall, excellent work. I would just encourage you to tie those requirements back to fundamentally, I need to process 10 images per second, I need to climb a 40% slope, whatever, that's your real requirement.
All right, thank you, sir. And with that, we do need to let the other robotics team in here talk to you guys about their fantastic arm, but we will be with our poster all day, so please feel free to come by and ask questions then.